Okay, what we're going to talk about today is how to calculate an area under a curve. The problem with making an accurate calculation of a curve is it's curved. It makes it a little tricky to know what the area is. So let me just kind of give you a visual what we want to accomplish right now for this goal. Basically from 0 to 6, and I'm not going to shade it, but from 0 to 6, I like to calculate the area that lies underneath this curve but above the x-axis. So, what we're going to do is an approximation technique using rectangles. Now, the question becomes, how many rectangles are we going to use? And I'm going to start the process by doing 2 rectangles. Then we're going to jump up to 6 rectangles. And last but not least, we're going to jump up to 12 rectangles. Now, I'm going from 0 to 6. I can make the rectangles of any width I want to, but we're going to keep it standardized. If I'm going to split it into 2 rectangles, I'm going to make the width of the rectangles equal. So, I'm going to split my graph exactly in half. Between this wall and this wall, I'm going to place 1 rectangle. And between this wall and this wall, I'm going to place my second rectangle. The first technique I'm going to use is a left-hand sum technique. Now, to do a left-hand sum, what we have to do is look at rectangle number 1. Notice, rectangle number 1, I'm looking for the area above here, but below there. I need to determine appropriate height. A left-hand sum technique is quite simple. I go to rectangle number 1, and I go to the left-hand side of it. I see where it connects to the graph on the left-hand side. So, on the left-hand side of this graph, it connects about there. And this will be rectangle number 1. It's very easy to calculate the height of that rectangle. All I need to know on that rectangle is how wide is it. And my rectangle has a width of 3. And this particular rectangle has a height of approximately 5. So the area of this first rectangle is going to be about 15 square units. Now I'm going to move to my second rectangle. I'll identify 3 sides of the rectangle: the bottom, the right-hand side, and the left-hand side. We're going to use for our technique the left-hand side. So I go to the left, I see where it touches the graph, and I put my height right there. And now I have all 4 sides of my rectangle, noticing that this rectangle number 2 touches the graph on its most left-hand side, the top of the rectangle. The top of the rectangle touches the graph on the left-hand side. So I will now approximate this rectangle's area. It also has a width of 3. Its height is approximately, if I had to guess, about 3.2. Then its area is going to be the product of those 2 numbers. 3 times 3.2, which is 9.6. To find an estimate of the total area, I'm going to add those together. And I end up with a total area of approximately, total area of approximately 24.6. I'm going to stick with the left-hand sum technique for a little bit. Now I'm going to convert, instead of having two rectangles, I'm going to convert to having 6 rectangles. I'm going to do that by taking each one of my rectangles and splitting it into 3 pieces. I should be doing that in black. I guess it doesn't really matter. Now, notice I have 1, 2, 3, 4, 5, 6 potential rectangles there. I'm going to find each rectangle by taking a height where it touches the graph on the left-hand side. So, notice my first rectangle. I find where it touches the graph on its left-hand side, and I make that its height. And this is rectangle number 1. I go to the second location for my rectangle. I see where it touches the graph on the left-hand side. The height of the rectangle must touch the graph on its left-hand side, and I make a rectangle. Rectangle number 3, I will do the same thing. I will connect the rectangle on its left-hand side. It's not going to change it from the last height it had. I'm going to go to rectangle number 4, and I'm going to connect it on its left-hand side. So the top of the rectangle touches on the left of the rectangle. Rectangle number 5. I will go to the left-hand side where it touches and put the height there. Rectangle number 6. I will go to the left-hand side and put the rectangle there. Notice my now 6 black rectangles have come much closer to the shape of the area under the curve. So, now I have 6 rectangles. I'm going to calculate the area of each one of these. These are nicer because every one of these rectangles has a width of 1. So to find their area, I just need to know their height. The height is the area because the width is 1. So the area of each rectangle's piece, the first one's area is about 5. The next one is about 5.6 if I had to approximate, and I am. The next one has about approximately 5. The next rectangle's height is about 3.2 approximately. The next rectangle's height is approximately 2.2. And the last rectangle's height is about 1.6, I will say. If I add the area of each one of those individual rectangles, it'll give me a good approximation of the actual area under the curve. given me a total net area. I'm going to move this over a little bit. Total area of about 22.6. Oops. Things get tricky. Okay. That is a left-hand sum technique. I'm actually not going to split it into 12 just for the time consuming and do the calculations. I will, however, so you can see the visual impact of what happens when I make 12 rectangles. So, if you'll notice now when I split each one of these rectangles in half, let's see, do I have another colored pencil? I got a green felt tip. Rectangle number 1, it doesn't affect the first rectangle, but the second one. Notice, this second rectangle now is much smaller than the actual height of the graph. But when I make my new rectangle, it's much closer. The first part of the old rectangle number 2 is not affected, but the second part is. Notice now the second part of the old rectangle was a little too high. The new one's coming down. The old rectangle number 3, the first half of it stays. The second half comes down. Make this one a little bit more better highlighted, the first one, and this one better highlighted. Now, first half of rectangle 4 stays the same. The second half comes down a little bit. Rectangle number 5, first half stays the same from the old one. The second half comes down. Rectangle number 6, the first original half goes down. Second half, stays the same. The second half comes down slightly. And now my new object, notice, where originally I was too high, as I made more rectangles, it came down. Where I was originally too low in here, see the original blue one in there? Those areas now have gone up. So any place I was originally underestimating, I am underestimating by less. Any place I was overestimating, I am now overestimating by less. As we produce more rectangles, we get more and more accuracy. Okay, for this next example, same idea. I'd like to take the area underneath this curve. In this case, the curve is going to go from 0 to 5. And that's all I'm interested in, taking the area from this curve. In this, I'm going to use 2 separate techniques. Actually, it's going to be a total of 3 separate techniques. One is going to be the left-hand side. The other is going to be the right-hand side. And last but not least, I'm going to use a technique called the trapezoid technique. Okay, so first technique we talked about in the last problem. So I'm going to make this with 5 rectangles. So n is the number of rectangles.
Is that something given?
So, and if I have a total of 5 rectangles, then the width of each rectangle is going to be 1. Notice these are x values. And I calculate that x, the distance of each rectangle, the width of each rectangle. No matter which one I look at, I can calculate the width of that rectangle by taking the second x value minus the first x value. I've got a symbol for x2 minus x1 we learned in algebra. We refer to that as delta x, which is how wide each rectangle is going to be. So, for this one, the width of each rectangle is going to be 1. Because no matter which rectangle I look at, if I take x2 minus x1, I still get a width of 1. So, first to the left-hand sum. I'll show that in black. Connect the height of the rectangle where it touches the graph on the left side. Connect the height of the rectangle where it touches the graph on the left side. The height of the rectangle where it touches the graph on the left side. Continue this procedure, touching only on the left side. Since each one of these has a width of 1, I can calculate the area of each individual rectangle by simply multiplying by the height. So the first rectangle has an area of 2. The second area is approximately, I would say, about 1.2, because this is 1.5. Third rectangle has an area of approximately 1. Fourth rectangle, maybe 1.4. 1.3, 1.4, only an approximation. And the fifth rectangle has about 2.25, approximately. I could add these up, and these would be my left-hand sum. So, let's see what we get. 2 plus 1.2 plus 1 plus 1.4 plus 2.25 is about 7.86. Right-hand sum technique is pretty similar to the left-hand sum technique, except for instead of on rectangle number 1, I'm connecting the top where it connects to the graph on the left. I'm going to connect I'm going to make the height where it connects on the right. And this one's going to be connected on its right. This one on its right. This one on its right. And this one on its, oops, went off a little stray there, on its right-hand side. So if I look at those blue rectangles, what I should notice about the blue rectangle is the first one is the same rectangle as this black one is next to it. They both have an area of about 1.2. This blue one is the same as that black one. Both have an area of 1 approximately. This blue rectangle is the same size as this black rectangle. Both have an area of about 1.4 square units. This blue rectangle is the same height as this black rectangle with a height of about 2.25 units. And now I have one new rectangle. I need to figure its height out. It appears to be about 3.5. When I add up these rectangles, I get an approximation of my area of 1.2 plus 1 plus 1.4 plus 2.25 plus 3.5, giving me a total area of approximately 9.35. The third technique is called the trapezoid technique. Now, a trapezoid, basically, what I'm going to do to make my trapezoid is I'm going to connect it on both the right and the left, and I should probably use maybe a green color, and I'm going to make a trapezoid. On the left I'll have this column, bottom is my width, right is this column, and my trapezoid connects, making that object. So here is my first trapezoid. Now, as you can see, that trapezoid is very close to approximating that curve, but it's not the same, but it's much closer. Everyone okay with that? The next trapezoid, I connect it both on the left and right hand sides where it touches, and connect the dots. The next one, I connect on the left and right hand sides, connect the dots. The next trapezoid on the left and right hand side with a straight line, connect the dots. And last but not least, left and right hand sides, connect the dots. I have 5 trapezoids. To calculate the area of these 5 trapezoids, the easiest way is actually just to simply take the left hand side plus the right hand side and divide by 2. It will give you the exact same as using the base 1 plus base 2 times width divided by 2, which is your trapezoid area technique. So, but an easier method, average these two values. So 1.2 plus 2 divided by 2, that first trapezoid has an area of 1.6. The second trapezoid is 1 plus 1.2 divided by 2, has an area of 1.1. The next one has an area of 1.25. Next one, I'm going to have to calculate that. 2.25 plus 1.4 divided by 2 is I'll round to 1.8. And last but not least, 3.5 plus 2.25 divided by 2, and I'll round this one also to, I'll round it to 2. I'll call it 2.9. I'm rounding. These are all approximations. You should understand that anyhow. Third trapezoid should have been, third trapezoid should have been 1.2, not 1.25. Little mistake there. So my trapezoid technique then is going to have an area that approximates the curve with 1.6 plus 1.1 plus 1.2 plus 1.8 plus 2.9, which is approximately, trapezoid technique, approximately 8.6. There's an actual easier way to get the trapezoid technique. If you have the left-hand sum technique and you have the right-hand sum technique, instead of doing it column by column, I can just simply take the 7.86 plus 9.35 divided by 2, and I'll still come up with the 8.6 as my approximation. So add these, divide by 2, gives you your trapezoid technique, which, as you can see visually, becomes a very accurate approximation of the area under a curve. If I want greater degree of approximation, I need more rectangles.